morning. This is the Daily Space for today, Thursday, August 13th, 2020. I am your host, Beth Johnson, and I am here to put science in your brain. After the news today, we will be joined by Georgia Tech postdoc, Dr. Kynan Hughson, to go more in depth about this week's amazing wealth of publications on the dwarf planet Ceres, which has been found to have a subsurface briny ocean and possibly active cryovolcanoes. I am a huge fan of cryovolcanoes, so I'm very excited to speak with Dr. Hughson. Before we get to the news, though, I want to give you all a heartfelt thank you for being kind, supportive, and welcoming last week as a new host. I feel less terrified this week as a result. We have a truly wonderful community, and I'm proud to be part of it. And now for the news. Since this week's planetary news has been dominated by Ceres, we decided to share some recent mission updates that are related to planetary science. This being 2020, not all of those updates are good news. Let's get the bad news out of the way first. On Monday, a 3-inch auxiliary cable at Arecibo Observatory snapped, whipping through the dish panels and causing a 100-foot gash. While this sounds incredibly awful and the photo is striking, the cable damaged only 250 panels, a mere 1% of the total dish. However, and there always seems to be a however this year, the Gregorian dome above the dish also suffered some damage, as did the dome's access platform. While the dish can be used at a decreased sensitivity with holes in the surface of the primary reflector, the damage to the dome has to be repaired first. Operations have been suspended as a result. The observatory's director, Francisco Cordova, stated, "We have a team of experts assessing the situation. Our focus is assuring the safety of our staff, protecting the facilities and equipment, and restoring the facility to full operations as soon as possible so it can continue to assist scientists around the world." Arecibo, which is operated by the University of Central Florida, has been in operation for 50 years and has managed to survive countless hurricanes and earthquakes. The facility was still under repair from Hurricane Maria in 2017. In spite of the ongoing repairs, Arecibo was giving us great science, and as recently as Monday, we reported on the discovery of a new near-Earth asteroid imaged by the observatory. We are continuing to monitor social media for more information and updates. At the time of writing, the estimates we have seen have ranged from a minimum of 2 weeks to several months to a year. This is a hard blow to radar and radio astronomy. And now for the good news. On Tuesday, NASA's OSIRIS-Rex spacecraft performed a final dress rehearsal in preparation for sampling our favorite asteroid to hate, Bennu. To collect a sample from the surface of Bennu, OSIRIS-Rex must perform 4 maneuvers, and the dress rehearsal covered the first 3. First, the spacecraft performed a deorbit burn to get out of its safe home orbit and reach the asteroid. 4 hours later was the checkpoint burn, where the spacecraft checks its position and velocity and then adjusts its downward trajectory to approach the surface. 8 minutes after the checkpoint burn was the match point burn, which is when OSIRIS-Rex has to match its rotation to Bennu's in order to fly in tandem with the asteroid above the Nightingale sample site. All 3 of these burns went well, and the spacecraft performed a back-away burn to end the rehearsal and return to its safe orbit. Keep in mind that all the commands must be sent in advance due to the 16 light minutes distance from Earth, and OSIRIS-Rex functions autonomously once the go command is given. Also, per the press release, during the rehearsal, the spacecraft successfully deployed its sampling arm, the Touch and Go Sample Acquisition Mechanism, TAGSAM, from its folded, parked position out to the sample collection configuration. Additionally, some of the spacecraft's instruments collected science and navigation images and made spectrometry observations of the sample site, as will occur during the sample collection event. You can see the newly acquired images of the Nightingale site in the animated GIF here and later on our website at dailyspace.org. And we will be waiting along with all of you for the actual sampling in October. Last but not least, we received news that NASA's TESS mission completed its primary mission on July 4th. TESS, the Transiting Exoplanet Survey Satellite, has surveyed almost 75% of the sky during this first 2 years of operation. The satellite, for those unfamiliar, uses changes in the brightness of stars to detect the transit of planets across the surface of those stars. So far, scientists have found 66 confirmed exoplanets and over 2,100 candidate exoplanets in the data. TESS has now entered into the extended portion of its mission, turning to finish surveying the southern sky through September 2022. Several improvements have been made as to how the satellite collects and processes data. Per the press release, its cameras now capture a full image every 10 minutes, 3 times faster than during the primary mission. A new fast mode allows the brightness of thousands of stars to be measured every 20 seconds, along with the previous method of collecting these observations from tens of thousands of stars every 2 minutes. The faster measurements will allow TESS to better resolve brightness changes caused by stellar oscillations and to capture explosive flares from active stars in greater detail. Congratulations, TESS. We will continue to expect great results and will bring them here to you on the Daily Space. And that rounds out our news for today. This has been your Daily Space. Today's episode was written by me, Beth Johnson. Engineering is provided by Ali Pelfrey, and web content is produced by me. Our executive producer is Dr. Pamela Gay. You can get a complete transcript, show notes, and see images related to each of our stories at our website, dailyspace.org. We are a production of the Planetary Science Institute, a 501c3 nonprofit dedicated to exploring our solar system and beyond. We are here thanks for the generous contributions of people like you. The best way you can support us is through patreon.com/CosmoQuestX. And make sure if you listen to our podcast, you review us. Your reviews wherever you listen will make it easier for others to find this show. Please help grow our community. Like, share, they're free. You never know whose life you can improve with a daily dose of science. And now we're going to take a quick pause while we get set up to bring in Dr. Hughson. Welcome back. Joining us now is Dr. Kynan Hughson, a postdoctoral researcher at Georgia Tech. Kai has been studying the dwarf planet Ceres since his graduate years and helped with the geologic mapping of its surface. He is now part of the Dawn mission team, and his work helped establish that Ceres has abundant reserves of ground ice. He joins us today to talk about the recent release of 7 papers that provide evidence that Ceres has a briny subsurface ocean and possibly even active cryovolcanoes. Dr. Hughson, thank you for being here.
Hi, thank you for having me.
So tell us about your work a little bit. What has been your role in the Ceres, in the Dawn mission Ceres research?
Sure. I go way back with Dawn, not back to the very started graduate work at UCLA about 6 years ago, and I was brought on by my PhD advisor, was Chris Russell, who was the principal investigator for the mission. So it was the right time and the right place to work with the principal investigator of a spacecraft mission that was actively ongoing, and it was an amazing experience. So my background is physics and geology, terrestrial geology, um, with a particular interest into glacial and glacial geologic processes. And I was brought in to the team. We hadn't even got to Ceres yet. That was prior to March of 2015 when we got our first images back. So we really had no idea what to expect except from some of the prediction models and some grainy images from the Hubble Space Telescope. But it really was a brave new world we were about to explore. So we got there with no preconceptions, and that's an amazing thing to be as a graduate student. Just have this blank slate that no one knows anything about, and you get to dig your teeth in and go to town and uncover some things that no one thought would exist. So that was my involvement. And the first thing we did was get into the geologic mapping, understand what the surface looked like, what it was made out of, what features existed there, and then to dig at those features and to dig at the geology and dig at that composition and learn as much as we could about how this dwarf planet was created and formed, what it's made out of, and how it works, and what cool things the surface can tell us about what lies just beneath the surface.
Wow, that is great. I was a graduate student myself and did it in terrestrial geology, so I completely understand the joy of going in and not having all these preconceived notions to deal with. So I'm a little envious. I'm possibly a lot envious, but that's okay. So when you were working on it, I know, like you said, you've been doing this since your graduate years. What was really like the first thing that made you go, this place is a lot more interesting than just, hi, it's an asteroid and it's a pile of rock?
So Ceres is super cool for a lot of different reasons. But we knew Ceres was going to be something new before we even got there. It's just weird. Ceres itself is the largest asteroid in the asteroid belt between Mars and Jupiter. It's so big, it's surrounded by its own gravity. It's classified as a dwarf planet. It's the only dwarf planet in the inner solar system. It's about 1,000 kilometers across, which makes it about as wide as the state of Texas. It's it's pretty big, and it's super massive. If you took just Ceres by itself, it would be about a third of the mass of the entire asteroid belt. All of the asteroids out there, it's 1/3 of all of them, essentially.
Wow.
It's a planet in its own right. Um, so we didn't really know what to expect. We know its density was low before we got there compared to other large asteroids. So there was some ideas about it being rich in water or rich in ice, and others thought it might be rich in organics or full of pore space, just empty like a big sponge that made it so light. Um, and this led to a lot of predictions about what the surface might look like. And some particularly interesting ones thought it would be rich in ice. If that ice was near the surface, that there would be no impact craters on the surface, or it would be very smooth because all those impacts would relax away because warm ice flows over time, kind of like how a glacier flows down a mountain. So any big pits would kind of smooth out until you get this billiard ball sphere. But the surface of Ceres was super cratered, like with a lot of craters.
Right.
Um, but the interesting thing was that they're weird shaped. They're what we call complex craters. So instead of being a simple bowl shaped, they have a lot of central peaks. So this material that sticks back up in the middle of them, sort of like how when you drop water into a pond, there's a bit of a rebound and that ripple comes up and it's frozen in place in these craters, and there's these terraces. And when we saw all those small complex craters on the surface, we knew that there was something was up, because that's not what other big asteroids are like. Like Vesta, the other big asteroid that Dawn went to, is made mostly of rock and has all these simple bowl-shaped craters. So when we saw that there weren't really those bowl-shaped craters, that there were mostly these small, complex craters, that's when we knew that there was something interesting going on beneath the surface, something weird, something that made it weak and different.
So what methods did you use to get at figuring out what was causing these complex craters to form this way?
The Dawn spacecraft was equipped with 3 major science experiments and a big radio antenna that it uses to communicate with the Earth, which also lets us understand what the gravity field is like. So between understanding the gravity from tracking the orbital motion of the spacecraft and using cameras to look at the surface structure and geology, we also had a visible and infrared mapping spectrometer, which is a really fancy camera that lets us decompose the wavelengths that we're looking at of the surface into hundreds of bands. So it'd be like a camera, instead of being able to see red, green, and blue, like kind of what our eyes do, instead you see 440 different colors. And each one of those things can tell you a little bit about how the surface is reflecting light, and that in turn tells you about what the composition of the surface is, what materials, what minerals are on the surface. There was also a gamma ray and neutron detector, which lets us peer below the surface. So when that happens, when cosmic rays smash into Ceres, they'll break apart some atoms and they'll cause neutrons and other particles to fly off. And through a little bit of nuclear physics magic, if you know what the energy of those neutrons are when they hit your detector, they actually tell you what the elements of the surface were, up to about a meter below the surface. So combining those spectrometers that tell us about the elements and the minerals on the surface with these cameras that let us image the surface and this geologic structure and the gravity, which tells us what Ceres' layers are like and how dense its material is and where it's situated, we can form this picture, this kind of holistic picture of what Ceres is like from the deep interior up to the very surface layers. So
That
those are
is
very generally, those are the techniques we use.
that is fascinating. I mean, that's just amazing to be able to go visit a distant world and learn all of this from one space mission. I'm really impressed with the results. When this was all being sent back to Earth originally, when Dawn was actually there, one of the things that was very fascinating to the public, of course, was the bright spots in the craters. Um, what was your take on that initially, and what did you learn over the course of doing the research?
I love that question, because that's almost got like a historical perspective on it, because we went through stages of understanding when we first saw these bright spots, and the evolution of our thinking and our understanding of them has changed so much that it's just funny to go back and look at what we thought and what we did and where we are now. Um, so those features, those bright spots, they're called, the official name for them now are faculae, which is Latin, which literally means bright spot. So it's not even very creative. Um, but these faculae that we see on the surface pretty much only exist in one crater. I mean, these little bright spots exist over the whole surface of Ceres, don't get me wrong, but there's only one place where they're big enough that you can really see them from far away. And those are the special ones inside of this large 92-kilometer diameter crater called Akator. Um, and those were so big and so bright that they were actually seen in the Hubble images before Dawn even got there. So we had an inkling that something weird was going on right there, but we didn't know how weird it was until we got there. And of course, these are the first major things that were discovered from far away, and they just kept getting more fascinating as the spacecraft got closer and closer. So initially, um, everyone was interested into what they were, and the science team is divided on, are these things, are they light minerals, like clay minerals? Are they light minerals? Are they salt deposits, like a salt flat in Death Valley that's white and reflects a lot of light? Or is it pure ice, like a giant skating rink, just reflecting all the surface, like the surface of Enceladus? Um, and and we didn't really know, and we didn't really know for almost a couple years, essentially, until we get close enough that our spectrometers could resolve these individual spots without being contaminated with all the material that was next to them, because they're pretty small. You have to get pretty close so that the camera only sees that portion, so you can detect what it is. And it turns out that this material is totally dominated by three different minerals, essentially. There's sodium carbonate is the dominant mineral, and that's sort of like it's like a limestone almost, except instead of calcium being the dominant metal, it's sodium, and that's a really weird mineral. It exists some places on the Earth, like in Death Valley in California and other really dry, arid environments where water evaporates
Right.
away and leaves behind this lag. But that's not in this quantity. This is probably the largest sodium carbonate deposit in the solar system that we know of so far. And there's also sodium chloride, so your regular old table salt is there in abundance, and ammonium chloride, another chloride salt, but this time it's ammonium instead of sodium. So this weird mixture of chemicals. And then there's some hydrated phyllosilicates, which is just a fancy word for your clay minerals, kind of the stuff you find in mud.
Right.
but
So
lots of water.
so lots of water. Yeah, if they're hydrated, then you have to have some sort of water source. So what led the team to figuring out that there was this briny subsurface ocean underneath that has somehow managed to come up to the surface and create these surface compounds, these salts and the carbonate and all of that.
A, a lot of different approaches, actually. So in with planetary science, especially with Dawn at Ceres, everything is what we call remote sensing science, essentially.
Mhm.
So we don't have a there's no astronaut on the ground. There's no rover with a shovel. We can't dig into the surface to find out exactly what this is, to look at it and say, "Yep, it's a rock." We have to rely on what we can see from orbit, and everything we can get. So we can't always get the definitive proof that we'd like to see when making a statement like, yes, this is for sure this thing, because we don't have a sample of the material that we can't look at ourselves. We can't run it through a mass spectrometer in $1 million lab on Earth. We have to take a picture of it and then deduce from that what it is. So instead of using one technique, like just taking images or just taking spectra, we rely on the synthesis of techniques. So we can take the gravity science, we can take the mineral evidence, we can take the element abundance from the gamma ray and neutron detector and combine that with the geology, the geomorphic context, these images that we take, and through that we can formulate and test our hypotheses against these 4 or 5 different observations, and the hypotheses that align best with the observations are the ones that we're most confident about.
Right.
So that's kind of how we get to this point. So for this material, this briny material and these materials on the surface, we see a lot of strange things that lead to this conclusion. We see these unusual minerals. So the mineral data tells us that there are these hydrated phyllosilicates, these things that need to form in liquid water. Essentially,
Right.
the chemistry we know from Earth chemistry, these salts and these silicate minerals need to form in liquid water. So you kind of need that from the get-go. That's where they were formed. That's how they were deposited. And we also see from the geology that these are concentrated in low-lying regions, which is not uncommon for what you would expect for, like, if you flood a salt flat, like in Death Valley. I'm going to come back to that for the third time today. And then you evaporate all this material, it 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 goes, and these lakes form in these low-lying regions, and as they evaporate, they go from the outside in, and they leave a characteristic pattern of all this material that's left behind as the water evaporates. And we kind of see similar patterns on Ceres in these faculae. And then there's the gravity data. And we know from the gravity data that there are these low density anomalies below Akator, which hint towards an abundance of porosity, or more likely an abundance of liquid phases like brine at depth. So we know that there's likely a concentration of liquid phases like brine or water, localized within the material below Akator. So that all three of those things start to paint a complete picture of how this material originated.
That's fascinating. And I love how the Earth analogs have to come into play because, of course, when we are doing all this remote sensing, we have to use what we know. And so we have to turn to Earth and say, okay, well, where do we see something similar and use that as a basis? So, I find Earth analogs great for this kind of thing. And it's so nice. I love Death Valley. It's amazing. So that's great that that was used in that fashion. So I promised you before we went on air that I was going to ask you about cryovolcanoes. So for me, I have focused mostly on icy moons like Europa and Enceladus. And for me, cryovolcanoes tend to be, hydrothermic vents at the bottom of these, subsurface oceans on these icy moons that are, to me, I mean, in my mind, basically larger than the hydrothermic vents we would see here, but more on the scale of volcanoes, but definitely not doing liquid magma, obviously. So, for you, what is your take on the cryovolcanoes? How does this? What is the cryovolcano definition for Ceres?
Well, I really appreciate that you kind of led me in with what your thoughts were on cryovolcanism, because cryovolcanism is kind of this nebulous term that's tossed around uh, often to mean a lot of different things to different people, and that's okay. Um, a lot of planets and moons are different out there, and we shouldn't exactly expect to see the same things everywhere. Um, but cryovolcanism has been used to describe everything from what you're describing to like the hot hydrothermal systems in otherwise cold environments to the geysers that are erupting on Enceladus and potential plumes on Europa to constructional features on Titan and then Ceres. Um, so there's a lot of different things that fit under all of those planets and all of those moons that um, could be considered cryovolcanic. But when I think cryovolcanic, uh, I think I think of something that is done in an analogous fashion to volcanism on the Earth. So that is, you have some molten phase, sort of like on the Earth. It's almost always some type of silicate melt, so molten rock. In very rare instances, you can get molten carbonate. There's only one existing carbonatite volcano left on the Earth, which is fascinating in its own right. And
Right.
then the stuff melts and it becomes buoyant because everything else around it is more dense, and then it's forced to the surface where it erupts and cools. You can also get intrusive volcanism too, where it's or magmatism, where it doesn't quite reach the surface, but it comes close and then will solidify. Um, but on Ceres, um, we don't really know how that would play out exactly. There's a famous problem in the icy solar system, whereas if you melt water, it actually becomes more dense than ice. So then you have this problem of how do you force something that's more dense than ice upwards? The physics is hurting you rather than helping you, like it does on Earth. And water likes to sink, which is why Europa and Enceladus have these nice ice shells on top of a liquid ocean. Now, it's a little unclear if that would still be an issue on Ceres, because it has a lot of other materials in its upper layers, upper crust, like light silicates and salts and carbonates. But it's still very low density. So a molten brine or a liquid brine would be probably similar in density, maybe a little less dense than what we see in the surface of Ceres. Um, but nevertheless, we observe these features on the surface, both in Akator and outside, these large mounds, domes, and hills that don't seem to be associated with impact craters. Um, and there's been a lot of speculation based off of the types of minerals we see on them, mostly carbonates and hydrated phyllosilicates, these hydrated clay minerals, that they could be sourced from a brine at depth. And Akator is this particularly weird instance of this. Um, because we have this anomaly of this gravity around it that suggests that there's these fluids at depth. But then we also have all of this massive impact crater, which deposits a lot of energy right away. That melts a lot of materials. So you've got these competing reservoirs. You have this melt and liquid created by an impact crater, and then you have this melt and brine at depth. And how they're going to interact and what types of landforms they create um, are going to be very similar. So part of the problem or interesting scientific question for Akator is there are these central faculae, these big domes, and then there's lots of domes separated within the crater in different regions, and trying to tie out, are they related? Are they created by the same reservoir? Are they created by freezing water at all? And then trying to tie the timing all of those together to understand its history. And are very detailed and difficult problems, and we try to address that a little bit. I'll take a break there because I realize I talked for a while.
No worries, no worries. I'm really interested, and I'm sure our audience is absolutely fascinated. So we're getting kind of close to the half hour here, and I wanted to ask you sort of one last question. So what's next in this research for you, for the team? What are you hoping to still find out? That was 7 papers of a lot of information. So what do you feel is left? Where are you guys going with it now?
Sure. I There's still like an entire history of series out there in the Dawn data that hasn't really been touched yet. That's a treasure trove that scientists and investigators will continue to look at for years to come until inevitably, fingers crossed, we go back there, this time with a lander to check out what these things are actually made of. Are they home to these cryohydrologic systems? Are they full of water and ice and organic compounds, which we found as well? And are these places that are relevant to astrobiology and habitability in the early solar system? But all this data, all of the Dawn data, is publicly available on NASA's planetary data system. Anyone can go out and download any of these images and any of these models and do whatever they want with it. It's amazing. But the mission itself is officially done. The final extended mission ended last year, and with the publication of these papers, that's the end of the formal mission, so to speak. And it's not that the team members are going their separate ways. We'll always be talking to each other, um, but um, but the money has run out, so to speak, and everyone's on their different business. So everyone likes to go in their different directions and do their own pet projects and use their own tools to understand Ceres. So, but Brittany and I are doing, my current postdoc supervisor at Georgia Tech, we're really interested in pushing the limits of this high resolution image data down to 3 meters per pixel. That's the highest resolution, which is incredible, of the
Wow.
surface over this large crater, and understand the detailed geology, particularly of these small hills that are really unique to Ceres. We don't see them on other asteroids. We don't see them on lunar craters, not in the same shape. And they're kind of similar to these ice cored hills that form in periglacial, so Arctic environments on the Earth, and maybe on Mars, called pingos. So they're kind of like giant snow cones, and they form when water freezes and gets pushed up to form these kind of conical hills. And they kind of sit on top of these layers in places where other processes shouldn't really be acting. So we're looking forward to using combination of the dawn data, the image data, and the gravity data, and the topography data to really understand how these forms, and we can compare them and contrast them with other types of hills we see on Earth and Mars, like cinder cone volcanoes and pingos, to try to understand really what's creating them and what that tells us about the material that underlies them, and how that informs us about how we should be thinking about volcanic and hydrologic processes on Earth and Mars, um, and what that tells us just about how these processes act across the solar system, and how to use those for understanding water and finding water in the future.
Wow, that's great. I'm really excited, and I hope that you and Brittany keep us informed on what you find out. Obviously, when you next publish, we'll be covering that here, and I'll be definitely interested in having you return to talk to us then. So thank you so much for joining us, Dr. Houston. I really appreciate the interview.